All right, 4.7 is types of chemical reactions. We've touched on some of these already. We've talked about different types of reactions. This is kind of a review of one of the previous units. But we have composition or synthesis. I typically call it synthesis. It's where you take two things and bring them together into one. Decomposition then is where you take one thing and break it down into two or more things. Single replacement, and this is what you did in your lab. You had copper sulfate here, and you had aluminum here. And that copper sulfate, the copper came out by itself, and the aluminum sulfate is what was created here, but it stayed in ion form, aqueous form. So then you were able to decant or pour that off, and you just left the copper behind in the end. And that's why it was the nice copper color when you were done. Double replacement reactions then are here, where they swap the locations of the anions or cations in this place. So here you've got lithium chloride and silver nitrate. They're aqueous at all times because you've got this is aqueous, and then this one obviously is because it's a nitrate. So then they swap partners. The nitrate goes with the lithium here, stays aqueous, and then it forms silver chloride here. Combustion of a hydrocarbon, then you've got your hydrocarbon, you've got your oxygen present, and so it looks like something like this. And then I guess that's not balanced though. And then here you would have just a combustion reaction with a metal, and then you're going to form a metal oxide. Okay. Double ionic replacement also includes acid-base neutralization reactions and precipitation reactions. All of these can be considered redox reactions, except for the double ionic replacement reactions. We're going to talk about redox. I think we get into that tomorrow, if I'm not mistaken. All right, so acid-base reactions are going to involve a transfer of one or more protons. So that's what we're looking at here is protons. So when we do acid-base reactions, we are changing proton locations. When we do redox reactions, we're looking at electrons. So when we get that into that tomorrow, you'll have that kind of framework to go by. So acid-base are going to be one or more protons are getting transferred. We talked in regular chem about Bronsted-Lowry acids and bases. So Bronsted-Lowry definition, protons are hydrogen ions. And when those hydrogen ions react with water, they're going to form what's called hydronium. Hydronium is H3O+. So we take a water, for example, we add a hydrogen ion to it, and we form this guy. In terms of protons, hydrogen ions and hydronium ions are often used interchangeably. So oftentimes, instead of writing this in, we just do this. Okay, because it's already in water. So when we look at these and we're trying to figure out what the definition of an acid and a base are, we look in terms of those hydrogen ions. Okay, so here, for example, we've got HCl. This H, it's going to get donated to this water and form this. So this is an acid, and this is the conjugate base of that acid. And what I tell people to do is look for the pairs. So these two look similar to one another. The difference is a hydrogen. Whichever one of these in the pair has more hydrogen is your acid. Whichever one has less is your base. And if it's on this side, it's called a conjugate. So conjugate base. Here, we look at these two. You can see that they look similar to one another. Which one has more acid? This one does, or more hydrogen. This one does. So that's your acid. It's on this side of the equation. So we call that a conjugate. And then that would make this the base. So the definition of an acid is that it's a hydrogen donor, and the definition of a base is that it's a hydrogen acceptor. We have certain substances that can act as acids and bases in different situations. Some things can't. They're one or the other. But other things like water, for example, water is, they call that amphoteric. So when it can be a, a proton acceptor or a proton donor in different situations, then that's called amphoteric. Right. Acids are described as being strong or weak. Okay. And what that means is how much of it is going to actually come apart to form hydrogen ions on the other side. Okay. Now, there is a difference between a strong acid and a concentrated acid, or a weak acid and a dilute acid. Okay. Strong acids, if they are dilute enough, don't cause any harm. Okay. Weak acids, if they are concentrated enough, can cause a great deal of harm. Okay. So just because it is a weak acid doesn't mean that it can't hurt you. Well, I mean, anytime you like, have you ever gotten lemon juice in a paper cut or something? I mean, stuff like that. Yeah. I am very, very, very cautious around here. Like, not everything scares me around here, but when I'm diluting acids around here, I glove up, I mask up, I goggle up. I mean, I do everything. Yep, because certain things scare me. Um, I've lost clothing to like it's eaten holes in my clothing and stuff like that before. So yeah, I tend to be very cautious with it. All right. So, what it means to be a strong acid is, and there's only 6 or 7 that you have to memorize. Okay. So, hydrochloric is one of them. What it means is when we have that hydrochloric, it is going to break apart completely into the two components. Okay. If you have a weak acid, so let's do like acetic acid. Okay. And we put that in some water. Very little of it is going to break up into this and this. And we denote that. Oops, shoot. Sorry. I, it's hard for me to talk and write at the same time and do it correctly. Okay. So we denote that this isn't going to go completely by doing a reversible arrow here. Because actually what's happening is we've got this and we've got it forming into this, and then a little bit of this actually reforms in, but very, very little of it. Here, if we were to draw this more realistically with our arrows, it would look something like this. Because most of it's going to stay in this form. Okay. A little bit of it's going to go this way, and you'll be able to understand how much of that actually goes over into this situation when we get into Unit 8. There's numbers that we give this, and that tells you how strong or weak an acid is. So you'll get quantitative values to go with that. But just realize that if you get this concentrated enough, it can cause problems. Just because they call it weak doesn't mean that it can't cause you any harm. Hydrofluoric acid, for example, is considered a weak acid. This will leach the calcium right out of your bones. Okay? And there's no stopping it. Like, they have to do amputations. It's so bad. Like, it's gone. So, like, just because it's a weak acid doesn't mean that it doesn't do harm. So just be very careful with stuff. Okay? Now, You've heard of pH before, probably, right? You've had me in class, you've heard of pH. pH then is the concentration. It's a scale using the concentration of these H values, okay? And what we do to that is we take that concentration, the negative log of the concentration of your H plus ions equals your pH. If we're looking in terms of a weak acid or base or a strong base, for example, NaOH is a strong base. If we wanted to figure out what's called the pOH, we do the negative log of that OH concentration. That's going to give us our pOH. If you add these two values together, that's going to equal 14. So the pH and the pOH of any given substance is going to equal 14. If you're given the pH and you want to figure out what the concentration is, you take 10 to the negative pH, and that's going to give you your concentration of your H plus ion. All right. Oxidation reduction reactions, and we're going to concentrate on these more as we move through. But what these do is they look at the transfer of electrons. So acid base looked at the transfer of protons. This is going to look at the transfer of electrons. So combustion is an important subclass of oxidation reduction reactions. It's where a species reacts with oxygen. In the case of hydrocarbons, carbon dioxide and water are produced when we have a complete combustion reaction. In some chemical reactions, there's a transfer of electrons between two substances. When this occurs, the reaction is considered a redox reaction. Oxidation refers to loss of electrons. Redox refers to gain of electrons. Okay, so I tell people this. This is how I remember it, is this acronym, OIL RIG. And that stands for oxidation is loss, and reduction is gain. So oil rig. There's also one that's Leo goes grr, like a lion. And that is lost electron oxidation, gained electron reduction. So if you like Leo better, I like this better, but this is just my preferred format. Okay. All right, good. So let's look at our reaction here with a redox reaction and learn how to work with these. Okay. So we need to figure out the oxidation number for each of these items. Okay. So my copper here, what is its oxidation number? +2. Yep. I have this 2 down here. This is a -1 for my nitrate. Now my nitrate, we've got to figure that out. So I'm going to come over here just because I have a little bit of room. What is my oxidation number for my nitrate? Net -1. So the overall thing for it is a -1. Okay. Oxygen, except for a couple weird, one weird kind of hiccup, which we'll get into, oxygen is traditionally a -2. Okay. So -2 times 3 is what? -6. Now our overall charge is a -1. So what does the nitrogen have to be? +5. Okay. So this is nitrogen is a +5. My oxygen is a -2. My sodium is by itself. So does it have a charge? No, there's no charge here. Copper's the same way. And then over here, this is a +1, this is a +5, and then the oxygen is a -2. All right, so we've got to see what's changed from side to side here. Is my copper's number the same? Is the oxidation number the same here and here? No. So my copper went from a +2 to a 0. In order for that charge to change, did it gain electrons or lose electrons? Gained. The number went down. Electrons are negative charges, so it gained 2 electrons to get here. So this is a gain. So if it gained, what lost? Well, my nitrate stayed the same on both sides, so that's not the culprit. So let's look at our sodium. It went from a 0 to a +1. So it lost electrons, right? So which one was oxidized and which one was reduced? Yep. In a oil rig. So oil oxidation is lost. So this one was the oxidized one. And this one, reduction is gain. This one was reduced. Okay. So if we look at what actually happened, if we look at our oxidation, kind of our net ionic equation here, did the nitrate change on either side? No. So we can get rid of that. But my net ionic, this changed because it went from a +2 to a 0. And this changed because it went from a 0 to a +1. We've got 2 of them to balance out the charges. Okay. So when we look at that, we can see kind of what happened. And that's what you've got to do is you've got to get comfortable with figuring out where these electrons are coming from, where they're going to, um, figuring out how to, which one's reduced and which one's gained. Now, if you remember back when I first taught you how to write these formulas out back in regular chem, we called these numbers oxidation numbers. Do you remember me calling them oxidation numbers? And you're like, why is it this is why it's an oxidation number. Now, why do they call it oxidation? Well, because oxygen was the first thing that they really discovered this happening with. When these metals were exposed to oxygen, they noticed that they started to corrode and started to change. And so that's why they started calling these redox reactions, and that's where the term oxidation came from. The other interesting thing is that this drives your thermochem. These oxidation reduction reactions are what make batteries work. And so when we get into unit 9, we're going to come back to these redox reactions and we're going to kind of tie everything together. So you'll be able to see how batteries work, and you'll even be able to see why certain terminals on batteries have a red terminal. So when you open up your car and you want to use your jumper cables, you notice how one of the terminals is marked with red. This is why. Because that's the terminal where this reduction is happening. Which is kind of cool, right? All right. So I talked about all of this as I was going through it. Any questions on this slide before we move on? All right. So oxidation numbers are assigned to each element. In the reactants and the products, this is an effective way to identify which one's being oxidized and reduced. One way to determine the substance that is oxidized or reduced is to look at the oxidation numbers. Every particle has an oxidation number associated with it. We went through that already. Oxidation number compares the number of protons with the number of electrons in that element. It is the charge of the element, and they're a way to track down who has the different electrons and where they're going to exchange to. Increase in oxidation number indicates that oxidation occurred, while reduction shows that reduction occurred. Why are you not advancing slides here? I know I've got more slides. There we go. All right, here's some of the rules. Oxidation numbers are always written above the element in question. They're always shown with charge, unless it's 0, of course. They are written for one of the elements in the question. The charge is always written first, followed by the value. That's not hypercritical, and I'm not great with this. So we're not going to have to worry about this too much. But typically you'll see it like 3+ or 1-. Okay. They will not mark you down if you do +3 and -1. So don't get too worked up about that. You can have oxidation numbers as fractions, but that's pretty rare. All right, so here are some more rules. Elements always have an oxidation number of 0. So if it's an element or a diatomic element, it's always going to be 0 for its oxidation number. Hydrogen in a compound is always +1 unless it's a hydride ion where it's a -1. Okay. So like for here, this is where it would end up being a -1. Oxygen in a compound, and this is the oxygen rules. Okay. This one's really critical. This comes up and they get you on this every once in a while. Oxygen in a compound is always a -2, except when it's in a peroxide ion. So, oxygen, oxygen, oxygen. Occasionally you'll see like hydrogen peroxide, and then it's going to be a -1. So this would be a +1. This would be a -1. Oxidation numbers for monatomic ions will always equal their charge. Oxidation numbers for neutral compounds should always add up to be 0. And the oxidation of polyatomic ions is the sum of their net charge. And I already kind of showed you one of those. All right, combustion reactions are examples of these oxidation reduction reactions. Products of the hydrocarbon reaction are always CO2 and H2O. So here you can see that this is a +1, this is a -2, +4, -2. So if this is times 2, I typically will start with the anion first, typically, or the last element, because typically that one is always assigned a steady number. This number for this guy in the front sometimes changes. So I will typically start with the second element in the compound and identify that before I move on. So we can look at those to see which ones oxidized and gained. So here our carbon changed from a -2 to a +4. So it did what with its electrons? It lost electrons. And our oxygen went from a 0 to a -2. So it gained electrons. And when we had that happen, then we look back at our oil rig. I literally say this in my head. Oxidation is loss. So this was oxidized, and this one would have been reduced. Precipitation reactions frequently involve mixing ions in aqueous solution to produce insoluble or sparingly soluble ionic compounds. And this is your SNAP, which some of you forgot on your quiz the other day. So be careful with that, because I had some people telling me that the think it was silver nitrate, that was your product. And if you would have paid attention to this, you would know that that couldn't have been your precipitate because it had nitrate in it. Precipitation reactions then are a subclass of double ionic replacements. They typically will result in an insoluble precipitate, and that often appears milky or cloudy. And it's going to settle to the bottom, and you can predict which products are of that by looking at those positive and negative ions. All right. One of them have a charge, you mean? Yeah, you'll typically have charges. Here's another example. Well, I mean, you didn't hear. I mean, they will over on this side, but one side or the other will have charges. Okay. Here's one: NaOH plus H2O. Okay. Now watch what happens with our water here in this one. Our OH, what am I doing here? Yeah, we're gonna make water out of that, right? No. What am I doing here? Oh, that's gonna split apart. This isn't a good example. What am I thinking here? Yeah. So this will form, yeah. So the hydrogen here is going to come over. It's going to form H2O. Okay. The sodium will just be a separate ion. And then you're going to form OH minus as your byproduct from this. That's what it is. No, that's not right either. I'm having trouble here, guys. Why is this not working out for me? Let's come back to that one. That's not a good example. Sorry. All right. Let's see here. So you've got some 4-7 stuff to work on. If you didn't get your lab in today, I want that brought in. And let me know if you got any questions.